have to compute in the process. So QR factorization, but the thin QR factorization just falls out of it. And people would use this method for computing the QR factorization, except it's so numerically unstable. If the columns of A are almost linearly dependent, the round-off error accumulation in this method is just terrible. It's better to use approaches I gave last week, like Givens or rotations or household reflections. There is a modified Graham-Schmidt that's a slight adjustment to this, which I won't get into today. It's in chapter 6 in the notes. But it's not really that much better. Household and Givens are still the best ways to do QR. Okay, so this is a general Graham-Schmidt algorithm, but now what I want to do is explain how it's used for generating an orthonormal basis for a pre-law subspace for iterative methods. So, similar idea, it's just that some of the details are different. So using Graham-Schmidt to generate an orthonormal basis for our pre-law subspace that starts with B, and we just keep multiplying it by A. Right, up to whatever dimension we need before we can stop our iteration. So first we'll have R0. So my notation will be a little different than what I did on the other board, but to be more consistent with what we're doing for iterative methods. But the concepts will be the same. So R0 is B, and then Q1 is R0 over its norm. Okay. And then by induction, so this is my base case that is written on here. So if I assume that I have vectors up to Q1, Q2, up to Qk are already made orthonormal, then how do I get Qk plus 1? So this is my induction step. So I compute Rk is equal to, first I compute Vk is just Aqk. So this is a vector I want to orthogonalize against all these. So then I compute Rk is Vk. So here's where I use the same main step as in Graham-Schmidt. So I have Qj, Qj transpose, Vk. So at least in here I don't have any lowercase a's. So keep in mind everything on this board is lowercase. If it looks like an A or a Q, you can't tell it's a Q. That'll be a little fixing here. Okay. And as I was asked about earlier, in the other algorithm I had a -1 here at the top limit, but I don't want that here because the idea is here I already have k orthonormal vectors, these guys, and I'm generating the k plus first one. So j will go from 1 to k. And now that I've done the orthogonalizing, I can just get the next vector in my set by normalizing it. Okay. So this procedure generates a set of orthonormal vectors that span my Krylov subspace, and it's in that Krylov subspace that I want to find my solution. Okay. And as I do in the notes, you can take the dot product of this equation with, say, q sub I, and verify directly that you'll get 0. Okay. Now, so for shorthand, I can define Hij to be equal to Qi transpose AQJ. And then this is for I strictly less than j. And then, actually less than or equal to. And then when I is equal to j plus 1, I define a little differently. It's just, ooh, dang it. Mistake in the notes. Should be the 2 norm of Rj. I have a P in the notes. I had P's originally, I changed them all to R's, and I forgot that one. Hopefully there are no more. Okay. Now, if I use this notation, keeping in mind that Vk is AQK, then I can rewrite my main Graham-Schmidt step as so I have AQJ is equal to the sum of HIJQI plus HJ plus 1J Q J plus 1. So this is just a rearrangement of this equation right here. So Vk, so really have, this is Vj, is AQJ. This summation over here became this down here using this shorthand. And then this term is the unnormalized Qj plus 1. So this is Rj right here. This is Dj over here. Okay. So now what I can do is this I have going on for j equals 1, 2, 3, and so on. So if I combine all of these, because what I have right here is a vector equation. So if I combine them to get a matrix equation, I get
Thanks.
I get A times the matrix Qj is equal to Qj times the matrix Hj, which has entries, these little h's, plus this next element. Oh. Sorry, K's here. Qk plus 1. Ek transpose. So what's going on here is both sides of this equation are an n by k matrix. So in this case, I want Qk plus 1 to be only in the last column. This term should have zeros everywhere else. So that's why I have this Ek transpose here, because this is 0, 0, and a 1 in the last position. That puts this in the last column. So as not to mess with the other columns in here. But then I can take all of this and write it as Qk plus 1 Hk tilde. Now, what are these matrices, these HKs? Well, capital HK contains all of these entries that I have here, the dot products and norms that I computed during this Gram-Schmidt process. So capital HK is H11, H21. So this matrix has entries in the whole upper triangle, but also has non-zero entries in the subdiagonal too. And everything below that first subdiagonal. So here I have the upper triangle. We have non-zero entries immediately below it. That first subdiagonal, everything below that is 0. And then HK tilde is a matrix that just has one extra row. So it's HK up top, and then in the last row I have EK transpose times HK plus 1K. I don't know if I'm going to do that. Okay. I realize I wrote this in the opposite order in the notes, but HK plus 1K is a constant, so it doesn't matter. Ashley, can you see this part of the board?
Yeah, I guess.
Okay. Not sure if I turned the computer or not. Okay. Now, this matrix that has non-zeros in the upper triangle and its first subdiagonal, but zeros otherwise, as a name, is called an upper Hessenberg matrix. And that's, we're going to see a lot of upper Hessenberg later in the course when we deal with eigenvalues. So it's important to keep this term in mind now. Although I did see some, in a paper once, a journal article, someone who, for whom English was not their first language, actually wrote that this was an upper Heisenberg matrix. But no, it's Hessenberg. Okay. So now we have this relationship among all of the orthonormal vectors that we're generating, which is slightly different than what happened in the Lanchos case. In the Lanchos case, we had this kind of relationship too, but this matrix, instead of being upper Hessenberg, was tridiagonal. So it had zeros above the first superdiagonal. So we had a much simpler relationship among all these vectors. But this is the best that we can get in this case where we don't make any assumptions about A. It's not symmetric, or certainly not positive definite. Okay, so now we know, if I go back to the beginning, our solution, our iterates xk is equal to qk yk. Well, we know how to generate the columns of qk now. That's just using this Gram-Schmidt process, this iteration. Now we need the vector yk that gives us as good a solution as we can get.